Shall we start? We shall start. Hello, everyone. My name is Chen-Yang Xu from Princeton University. So I'm the moderator of today's ICM section talk given by Tamas Hausel. Professor Hausel now is working at the Institute of Science and Technology in Australia. He has made a lot of important contributions to the study of modular space, including algeometry, topology, and geometry. Today, he will tell us about the enhanced mirror symmetry for Langlands dual Hitchin systems. Okay, please start.
Okay, so thank you very much for the local organizers to make this event possible and that I could give my talk here, and also ETH Zurich, which contributed to this event. And we're starting. Yep. And today I'm going to talk about enhanced mirror symmetry for Langlands dual Hitchin systems. In the first part, I will give a short survey of mirror symmetry phenomena in this subject, partly to give tribute to mirror symmetry, a subject which arose in physics and has been tremendously influential in algebraic geometry in the last couple of decades. I will concentrate on the moduli space of Higgs bundles, but I will import ideas of mirror symmetry to this setup. So let me start with how this mirror symmetry point of view was taken for Higgs bundles, the total space of the Hitchin system. So this first part will be fairly schematic. Things will only be vaguely defined. So we will take a smooth projective complex curve and the complex reductive group. And we will consider them in pairs with their Langlands dual group, denoted G dual. The main example for us will be just PGLN and its Langlands dual SLN. The moduli space of Higgs bundles, which is our main interest in this talk, the total space of the Hitchin system, was introduced by Nigel Hitchin in 1987 using gauge theoretical techniques, methods. And in algebraic geometrical point of view was Simpson's contribution starting in 1992. So we are going to consider the moduli space of semi-stable G Higgs bundles. A Higgs bundle is just a pair of a principal G bundle together with an auxiliary field, the so-called Higgs field, which is a section of the adjoint bundle of the principal bundle with values in the canonical bundle in the curve. The best view on this adjoint bundle, which is just the principal bundle in the adjoint representation, that the fibers are a copy of the Lie algebra itself. So whatever you can do with the Lie algebra, you can try to do it with the Higgs field as well. So the major player in today's talk is the Hitchin system, which is defined as a map from the moduli space of Higgs bundles. And in this generality, it's easiest to say that it is just the affinization map. So we take all algebraic functions on the moduli space of Higgs bundles, and this algebra turns out to be finitely generated. So its spec will be, in fact, just a vector space, half of the dimension as the original moduli space. And this is what is called the Hitchin map, which has wonderful properties. It is a proper and completely integrable Hamiltonian system. So this latter means that the fibers are Lagrangian with respect to some natural algebraic symplectic form on the moduli space. And properness implies, of course, that the fibers are projective varieties, Lagrangians, and in particular that the generic fiber, as in any integrable system, it has to be a torus, but this one has to be then an abelian variety. So generically, we have a fibration by abelian varieties, which will be important for our intuition. And this moduli space carries a lot of extra structures. So one of them was already, and basically everything was already in Hitchin's first paper, is a hyperkiller metric. In the gauge theoretical construction, there was a natural hyperkiller metric emerging. And in another complex structure than the one where we have this moduli space of Higgs bundles, there is an alternative moduli space description of them, of that complex manifold as the moduli space of flat G bundles. And in this setup, it was observed by me with Michael Tadeusz in 2003 for the group PGLN and SLN, and later the same was proved by Donaghy and Pantev in a paper which appeared in 2012 for all reductive groups, that one has, for Langlands dual groups, one has, first of all, an identification of the two Hitchin bases, and second of all, the generic fibers of the two Hitchin maps are dual abelian varieties in the original complex structure of the moduli space of Higgs bundles. But if you change the complex structure to this, sometimes it's called a hyperkiller rotation, so you change the complex structure, you get dual special Lagrangian fibrations, which is precisely the geometrical suggestion of Strominger-Yau-Zaslow in '96, which was proposed as a geometrical way to think about mirror partners for them for Calabi-Yau projective threefolds. But the same setup works for us because we have a hyperkiller varieties, in particular the RSO Calabi-Yau, and but we are in a hyperkiller situation versus their Calabi-Yau situation. But anyway, for us, we do have this pair of dual special Lagrangian fibrations. So that was the motivation. Geometrically, this pair of moduli spaces look like mirror partners. And in the beginning with Michael, we were searching for enumerative results, which could also prove or strengthen this view that these spaces should be considered mirror symmetric. So the first and the easiest, perhaps, aspect of mirror symmetry is that their Hodge numbers are in a certain relationship. And for us, this was what we call the topological mirror symmetry conjecture. We noticed that for small n, the Hodge numbers, certain stringy, gerby Hodge numbers, it took some time to come up with the right notion of Hodge number on these quasi-projective moduli spaces, that they agree. And this was really a non-trivial agreement. That's why we had to find PGLN and SLN different, a pair of distinct groups which are Langlands dual. And anyway, there were many technical reasons why this was the good class where to test this mirror symmetry. So we proved this for n equals 2 and 3. It is called, we already considered it as the topological shadow of equivalence of derived categories of coherent sheaves, something which will be more clear in the next slide. So from my perspective, in 2013, I proposed an attack on topological mirror symmetry using Engo's techniques on the cohomology of the Hitchin fibration, which was the heart of his proof of the Lagrange shells, that fundamental lemma in number theory. What I noticed is that the two geometries are uncannily related and similar. Very nicely, it was actually two of my former students, Michael Gröschenig and Dimitri Viss, together with Paul Ziegler, who eventually managed to actually find the proof of topological mirror symmetry, but with a completely unexpected technique using periodic integration, which is somehow conceptually simpler, perhaps, than Engo's original techniques. And they could turn this logic around, and they in fact could use the same technique to reprove Engo's main geometric cohomological result, again using these simpler techniques of periodic integration. And to have the full circle, it was completed by Maulik and Chen, who actually managed to prove topological mirror symmetry, this equivalent agreement of numbers on the two sides using the Engo techniques roughly along the lines, at least I was proposing back then. So it was a nice story, and it's exciting to see number theory and physics motivations in the same under the same roof. But today I'm going to talk about a different aspect, more involved aspect of mirror symmetry, namely originally with homological mirror symmetry, and then I will talk about enhancements. So it was physicists Kapustin and Witten monumental work in 2007, where they have proposed a physical understanding of these kind of mirror symmetries between Langlands dual Hitchin systems or Langlands dual flat connections. They actually argued that they can be understood from S-duality in four-dimensional supersymmetric Young-Mills. There is something they have had studied a long time before. And they argued that in this reduction, you can actually see the equivalence of derived categories of coherent sheaves on one side, which for them is the category of B-branes, and Fukaya category on the other side with objects, certain Lagrangians with some structure on them, which for them are what they call A-branes. And then in turn, they could argue, or they did argue on physical level, that this category should be thought of as the category of D modules on the stack of G dual bundles. And then they could, from this, deduce that the derived category of coherent sheaves on one side, on the moduli space of flat connections for one group, should be equivalent with the derived category of D modules, certain D modules on the stack of G dual bundles, which is the form, rough form of the proposal of Beilinson and Drimfeld starting around 95, which is what we can refer to, at least historically, as a geometric Lagrange correspondence. So this, since then, this has been refined by many people, Arinkin and Gatesbury in particular, and in GLN we have a much better understanding by now. But we'll just take this schematically as it is, and in fact, we are going to consider an even further simplification of these equivalences of derived categories. It is, this discussion was made in the paper of Donaghy and Pantev. They explain what they call a classical limit of this homological mirror symmetry. What they were doing is they were arguing that you can degenerate these two categories. This one, the derived category of coherent sheaves on the flat connection moduli space by taking lambda connections and sending lambda to 0, you can degenerate this moduli space to this one. You can take the same derived category of coherent sheaves on it. And on the other side, you can dequantize D modules, and you would get coherent sheaves on the cotangent stack of the stack of bundles, G dual bundles, which is roughly the moduli space of Higgs bundles. But anyway, we get now a more symmetric picture where on both sides now we have B branes, but in complex structure I, in the first complex structure. And also they had a very good understanding of this generically along the Hitchin fibration. So generically, they proposed that this duality should be given by Fourier-Mukai transform, because Fourier-Mukai transform gives us an equivalence of categories of coherent sheaves on an abelian variety, which is our generic fiber of the Hitchin map, and the dual abelian variety, which, as I mentioned, is nothing but the dual Hitchin fiber. So generically, we have this equivalence of categories on the fibers, and then we will do then this relatively along the Hitchin fibration. So generically, we have some sort of understanding of what mirror symmetry should be, this classical limit at least, and then the task is to be clever and try to extend it over the singular fibers. There are many things in this direction, but let me tell you the point of view that I have been thinking about. And again, this goes back to the work of Kapustin and Witten. They proposed two more enhancements to the story of mirror symmetry, which is somehow foreign to mirror symmetry. Both of them come from the origin of Kapustin-Witten's derivation of the mirror symmetry, namely the four-dimensional supersymmetric Young-Mills theory. So first of all, they proposed that we should consider in this story branes boundary conditions, not just with respect to one of the complex structures in the hyperkiller family, but in all of them at the same time. And so you could have brains which are, for example, type BAA, which are complex in the complex structure I, and the Lagrangian in the other two complex structures. Or we can also have BBB brains, which are complex in all the three complex structures. Okay, this is still today not 100% agreed among mathematicians what these things should mean, but roughly speaking, a BAA brain, at least as a support, should be something like a complex Lagrangian with respect to our algebraic symplectic structure, the modular space of Higgs bundles, while BBB brains should be something like a holomorphic vector bundle supported inside a hyperkiller subvariety on the other side. For us, we will always have space-filling BBB brains today, so it actually will be a vector bundle everywhere. And they actually propose that these type of brains should be swapped by mirror symmetry. And that's a pretty good help for mathematicians, because both of them are relatively restrictive. I mean, maybe complex Lagrangian is less restrictive. In fact, there are many complex Lagrangians, but the other side definitely is quite restrictive, this holomorphic, these hyperholomorphic vector bundles. And this is the first suggestion that we should consider hyperkiller brains, if you like. And the second is extra symmetries that they propose. So we have Taft and Wilson operators, which act as extra symmetry operators, which for us mathematicians will be certain, the Taft operators will be certain Hecke operators acting on the derived category of coherent sheaves. This is going to be a Lagrangian operator, a BAA type operator, in the sense that it's going to preserve complex Lagrangians. And on the other side, we will have Wilson operators, which are easier to define. They are just a tensor product of our coherent sheaf or complex of coherent sheaves with a vector bundle. And this vector bundle will be crucial later, so we will discuss it in a moment in more detail. And this actually is going to be a BBB operator, because basically this thing, this what we will tensor with, will carry already a canonical hyperholomorphic structure. And so if F also had it, then you would expect the tensor product will have it. So these are these two symmetry operators acting on the two sides of our mirror symmetry. And okay, before really claiming what they do for us, let me just be a bit more detailed here. So we will fix a point of the curve. Both operators are localized or using a point of the curve. And we will also fix the type of these operators, which will be a dominant co-character of the original group, which is just a dominant character of the Langlands dual group. So they are known to label the possible Hecke transformations on the vector bundles on one side, and on the other side, they are actually just using this representation to cook up this vector bundle. Namely, we will take a highest weight representation corresponding to mu for the Langlands dual group, and we will look at the universal G-dual bundle from the universal Higgs bundle, and we will look at it first in this representation. So now I have a vector bundle, and we will restrict it to the point C. And this will be now a vector bundle on the homological space. Okay, and the suggestion is that these symmetries intertwine or mirror symmetry, the S duality, in this sense, that if you first apply S and then the Hecke operator, it should be the same as first applying the Wilson operator and then S. And today we are just going to test it in perhaps one of the simplest coherent sheaves you can imagine is the structure sheaf of the modular space of the G-dual Higgs bundles. And then when you compute the left-hand side, you see that you will have to first compute the mirror of the structure sheaf. But fortunately for this, we have a hint from the Fourier-Moquet transform. Because what you need to think about, what happens with the structure sheaf when you do Fourier-Moquet transform relatively to the Hitchin system. And what you know about Fourier-Mukai transform is that the structure sheaf of the abelian variety will be mapped to the skyscraper sheaf at the identity in the dual abelian variety. And so at least generically, then the structure sheaf of the whole moduli space should be supported along the identity elements in each of the fibers. There is in fact a global section of the Hitchin map, which is called the Hitchin section. And that's a good guess. And in fact, it's expected that the mirror globally is going to be just the structure sheaf. This is what we call the Hitchin section. You will see the reason for the notation later. For the Langlands dual group. For the group, for the Langlands dual group. So this actually is in the, it's now we are back in our G side, so it's on the G side. On the other side, it's actually easier, of course, because we do know this vector bundle, tensoring with the structure sheaf does nothing, and we are talking about the mirror of this vector bundle in this representation given by this highest weight representation. So the mantra here is that the mirror of the universal bundle in an irreducible representation should be the Hecke transformed Hitchin section. And this is what we are going to study now in some of the simplest cases, how to determine what is the Hecke transformation of the Hitchin section. And then for now, let me just mention that this is always going to be at least supported at a finite union of Lagrangian upward flows. And so that motivates me to discuss upward flows. And so that's in the next slide. So we are going to consider Lagrangian upward flows in M. And we will now be more specific. We are going to talk about PGLN Higgs bundles, which is now just a pair of a rank n vector bundle defined modulo tensoring with a line bundle, and the Higgs field, which is just a traceless endomorphism of this bundle tensored by the canonical bundle. And the Hitchin map takes a much more explicit form. In this case, it's just the characteristic polynomial of the Higgs field, which will take values, the coefficients of the characteristic polynomial will live in these sections of the higher some powers of the canonical bundle. And so this will give us the Hitchin map. Then we will we'll consider an extra structure, even more extra structure on the Higgs moduli space. There is a C-star action by scaling the Higgs field, with respect to which the moduli space has this wonderful property, what I like to call that it is semi-projective, which means two things. That one is that the fixed point variety is projective, and second, that half of the limits of orbits make sense. So if I take any Higgs bundle and then I apply my group C star on it, the C star orbit will always have one closure point in one of the direction, namely at zero. We can always close down a C star orbit. So in that sense, it's just semi-projective. And for such varieties, we have a wonderful decomposition of the variety, partition of the variety into cells. And that's called, these are the things which are called upward flows. So I am going to consider now a fixed point of the C star action. And to this, we can collect all the Higgs bundles which flow into this Higgs bundle. And that is what we will call the upward flow from the fixed point, those bundles which flow down to this one when you apply the C star action. So there's the upward flow from E. And it has this beautiful property. First of all, that this is a locally closed subvariety, the location of these Higgs bundles, and additionally, that it is a cell. It is isomorphic in a non-canonical way to the tangent space at the vector bundle itself, the positive part of it. So it actually is true even with respect to the C star action. We have a model for this cell given by this infinitesimal picture. And in our case, we even have more structure because we have a symplectic form which behaves nicely with respect to the C star action. And this will imply that these things, vector spaces, in fact, will turn out to be Lagrangian, half-dimensional vector spaces covering the whole space because of the semi-projective property. We have this beautiful sort of polarization if you had studied symplectic geometry, and only sort of because the leaves are not all closed. If it was all closed, then this is pretty much what you would consider a polarization. Generically, they are going to be closed, and closed leaves play a central role. So in fact, we have a name for them, and they are called very stable. Either the Higgs bundle fixed by the cis direction, we call very stable, or the whole upward flow. If it's closed, this is what we call very stable. And there are various other ways to characterize very stable bundles. And one of them is to look at the Hitchin map restricted to this upward flow. So now this will go between vector spaces of the same dimension, will be C star in equivariant, and also equivalently to very stability, it will be a proper morphism. And in particular, this will mean this will be, in fact, a finite flat morphism. It's a beautiful, if you like, branched covering of the base. So generically, it's finite to one. There will be branches. It's a beautiful geometrical thing for the very stable ones. And in fact, this can be considered one of our motivating problems, actually in the work with Nigel Hitchin, and later that we have, we would like to understand the Hitchin map restricted to these upward flows. Can we somehow find coordinates on the upward flow where this map becomes explicit? And that's what we will be able to accomplish in a moment. But before I'm doing that, let me give you some examples of these very stable Higgs bundles, the ones which we can continue to work with later. So we will look at first, the first example will be a vector bundle together with the Higgs field. So the vector bundle is a direct sum of line bundles, these various powers of the canonical bundle. And we will look at, so if we will take a characteristic polynomial, an element in the Hitchin base, and to this we can construct a companion matrix, which is just a full nilpotent Jordan block, and together with the characteristic polynomial in the last column. So it's really just the companion matrix of this polynomial. And then things are arranged, these twists are exactly right, so that this actually will give us a map from E0 to E0 tensor KC. So this will be a Higgs bundle. It's a Higgs field of a Higgs bundle. We are first going to consider one of them, namely the 0 one, when all the A's are 0. And then it will be a nilpotent Higgs field. And this is our first, if you like, this is the most important Higgs bundle there is. This is called the canonical uniformizing Higgs bundle. And the name comes from the PGL2 case when in the flat connection picture, it actually gives us the hyperbolic metric on the Riemann surface. We can now study this in terms for very stability. Then you would want to look at the upward flow from this Higgs bundle. And the upward flow will be precisely these other Higgs bundles where with the companion matrices. So you will get one from each point in the base of the Hitchin map. And because of the property of the companion matrix, the characteristic polynomial of the companion matrix will be exactly the point A you are looking at. So it's going to be a section of the Hitchin map. And as such, you can argue that it is closed. And so this is your first example of a very stable Higgs bundle. In my mind, this is somewhere in the top of the whole Higgs moduli space. So the next class of very stable Higgs bundles will be using some elementary modifications of this canonical uniformizing Higgs bundle at a single point on the curve. So we will take a case elementary operation or fundamental operation. So that will be taking the same bundle as before, except to twist the last n minus k plus one of them with this OC. And we will also take this defining section of this bundle, which vanishes at C. And we change this single Jordan block, which was giving us the uniformizing Higgs bundle at a single element, namely in the kth column, that one we replace by this SC. And then you can follow it through that this will then define a Higgs bundle on this vector bundle Ek. So that's a elementary modification on the canonical uniformizing Higgs bundle. And our general result with Hitchin in our recent paper, shows that this is a very stable Higgs bundle. And in fact, we do it more generally. And so this is somehow the first interesting non-trivial example. But our proof is actually already was motivated by what we wanted to achieve, that we actually managed to prove that the upward flow, this upward flow from this Higgs bundle, which we will abbreviate like this, is nothing but the case fundamental Hecke transform of the Hitchin section. So you take these Higgs bundles, these ones, and you do at the point C a case elementary modification, which is allowed in the sense that you need to have the Higgs field preserving that subspace. You will do the transformation, and then you will get precisely the upward flow from this modified Higgs bundle. And then if so, you can actually use in a more conceptual way that this type of the Hecke transformation is labeled by the case fundamental character of SLN, which is a minuscule representation, smallest in a certain natural partial ordering among characters. And this ordering is exactly what's reflected in the natural ordering among upward flows if you start to close them down. And because it's minuscule, this one, it's a minimal with respect to this ordering, that conceptually says that the corresponding upward flow should also be closed. Okay, so that was the example. And now let me show you how to solve this motivating problem in this particular case by finding a surprising model of the Hitchin system on this upward flow as the spectrum of equivariant cohomology. So for this, let me quickly recall basics about equivariant cohomology. So G is a complex reductive group. We will consider the universal principal G bundle, where the total space will be contractible. The base space is what we call the classifying space. And we will take its cohomology with complex coefficients to be our cohomology ring, a base ring. And this actually can be explicitly computed as the polynomial algebra over the Cartan subalgebra, which are polynomials which are invariant under the Weyl group. And this is famously another polynomial ring. So our base ring is going to be a polynomial ring. So now we have a group action by G on a complex variety X. Then we can form the Borel quotient, we will define the equivariant cohomology as the Borel quotient, the cohomology of the Borel quotient. So the Borel quotient is just the diagonal quotient of X times EG, and as such it will map down to BG, the quotient of EG by G. So we will get a canonical map from the cohomology of the classifying space back to the equivariant cohomology. So equivariant cohomology is always an A star G algebra. We will also consider a subclass of actions, so-called equivariantly formal actions, where one way to define it is that you can recover the ordinary cohomology ring of X by restricting to the zero fiber, the maximal ideal of the origin in the quotient. Or equivalently, you can say that it is equivariantly formal if the equivariant cohomology is a free module over the base ring. You can also say that you can also take the even part of the cohomology, which will be a commutative algebra over C, and you can take its spectrum, and then the structure map will give a map down to the spectrum of the coefficient ring, which is just going to be T mod W, this vector space. And the equivariant formality will mean that this is proper. In fact, this also will give us, you can argue that this is also going to be finite flat. So you again have a very nice map, very similar to the Hitchin system on these upward flows. And even it could happen that this is going to be a vector space itself. And when it happens, it really is going to look like the the Hitchin map on an upward flow. And indeed, in this case of the minuscule upward flow I defined on the last slide, you can show that the Hitchin map on it is modeled on the spectrum of equivariant cohomology of the Grassmannian. So this modeling means that if you take the equivariant cohomology of the Grassmannian of complex k-dimensional subspaces of Cn, then this map down to the base, this finite flat morphism, models the Hitchin map in the sense that you have a natural evaluation map from the Hitchin base, and this is a pullback diagram. So you just pull back the equivariant cohomology and you will recover the Hitchin system on that upward flow. So that's a kind of surprising way to explain the Hitchin system on an upward flow, but it is nothing but the spectrum of the equivariant cohomology of the Grassmannian. So the proof is brings in a new way of studying equivariant cohomologies. It is by studying a certain natural fixed point scheme inside the Grassmannian. And the Grassmannian arises in all this because it's the affine Schubert variety of corresponding to this minuscule weight. And this is nothing than the space of possible Hackett transformations you can do at that point of this type. The k-elementary Hackett transformations are all possible k-dimensional subspaces at the fiber of that point. And now you have the Higgs field, so you want to make the Higgs field to preserve that subspace, and then that will give us a fixed point scheme in there. And then amazingly, we will find that this fixed point scheme will have a ring of functions, which is recovers the cohomology of the ambient Grassmannian itself. In particular, if you restrict this over zero, the zero fiber will be scheme theoretically a fat point. It's just it will be just a point over zero. That's part of a way to characterize very stable bundles, that the upward flow intersects the nilpotent cone in a single point, but single point is going to be a fat point. There will be a scheme structure, and because of this equivariant formality, we can deduce that that ring structure is just the ordinary cohomology of the Grassmannian. And this was somehow the starting point of all this circle of ideas. Originally, we discovered this with Nigel right after we finished our paper. So now I'm going to talk about two more things. One is on the mirror side, what will correspond by mirror symmetry to this equivariant cohomology. So this is some construction using highest weight representations of Lie groups. So we take a semi-simple Lie group in this case, and we take a highest weight representation to which we will attach a Kirillov algebra, which is tensor algebra, the direct tensor product of the symmetric algebra on the dual of the Lie algebra, tensor with the matrix algebra on the representation, and we will take G invariants. That's the way how Kirillov defined the algebra. I prefer to think of these things as polynomial maps from the Lie algebra to these matrices, which are G in equivariant. In either way, you can see that you can multiply with scalars. So if you have a G equivariant map on the Lie algebra, this will give us an element in this symmetric algebra. You can multiply here, for example, you have a map from G to here. If you have a G invariant function on the Lie algebra, you can just scale it. And so it is going to become an algebra with our usual coefficient ring, H star G algebra. Then Kirillov, one of his first theorems when he introduced this in 2000 is that this is commutative if and only if the representation is weight multiplicity free, when all the weights have multiplicity 1. In particular, when they are minuscule. So just like in our case, we have the minuscule representation, the case fundamental representation. And then you can use this Kirillov algebra to build what I call a universal bundle of algebra structure of the universal Higgs bundle along the Hitchin section. So we had seen along the Hitchin section how the universal Higgs bundle looks like. It's given by this companion matrix. And you can use the Kirillov algebra to build a bundle of algebra structure on this. That means that at every fiber along the Hitchin section, you want to define a multiplication. And so this can be done first by defining some matrices, namely you just take naively an element in the Kirillov algebra, which is a map from G to the matrices, and then map it the Higgs field we have at that point to this one, and then we will get a matrix. But more intriguingly, this is a very nice algebra. You can, in fact, identify the algebra with the representation itself. It will act on the representation in a cyclic way. There is a way to identify it with that. And using this perspective, you can actually define a bundle of algebra structure on the universal bundle in this representation, which, by the way, here is just the case exterior power of the standard representation, where we usually take the universal bundle already. And then if you do this, then you will have a very similar diagram as before. So we will take this bundle of algebra structure on the universal bundle along the Hitchin system, and we take a relative spec over the base. So the base is identified with the Hitchin base. And you just take the same kind of fiber diagram. So we have the same evaluation map at the point C. And then we have the spectrum of the Kirillov algebra. This, again, in our case, is commutative, so it's a nice scheme. And also is very nice. It's a finite flat scheme as before over the base. And you take the fiber product, and that's going to give us the spectrum of the universal bundle of algebras. So the construction, as I mentioned, is applying Kirillov operators and this property of cyclicity of the action, which was proved by Panyushev in 2004. So when k equals 1, this is just the bundle of algebra structure which appears in the BNR correspondence. In that case, you just apply the Higgs field and its powers, but you will get a higher BNR correspondence for higher representations. But that's another story. Let me finish now to equate these two last things, to argue that the enhanced Kapustin-Witten mirror symmetry in this particular example will give us something nice. In the case when G is PGLN and the representation is the case fundamental representation, then we know that we notice that the Hecke transformation is just itself this Lagrangian upward flow, this minuscule upward flow. It itself has a sheaf of algebra structure. You can multiply functions. And then you can think about what the sheaf of algebra becomes under Fourier-Mukai transform. It will be some sort of sheaf of convolution algebras, but over the identity, we will have an algebra structure. And that's what will give us this conjectural or hoped for universal bundle of algebra structure. And here is the final diagram where the two parts put together. So on the right-hand side, you see this modeling of the Hitchin system by the equivariant, the spectrum of equivariant cohomology on one side. And on the other side, you see this bundle of algebra structure, which we believe is the one which should come from mirror symmetry on the other side and in this picture. And then you can find this isomorphism, which is kind of beautiful because they are living on different sides of the world. So this one is on the PGLN moduli space, this upward flow, and this is the universal bundle for Langlands dual one. And we define this algebra structure, and then we took the relative spectrum, and you get this isomorphism because you can identify the bases by identifying the Hitchin basis. Actually is similar. You use the Killing form on the Lie algebra. You can also identify these two along the same way. And then you use one more result of Panyushev's, which shows that the Kirillov algebra for this particular representation is just the equivariant cohomology of the Grassmannian, even though he actually does it with SLN, he stays in the other side, but this picture shows that actually more conceptually we should take the Langlands dual group. But in this case, the minuscule and cominuscule varieties agree. But for example, type B and A, they are actually different varieties, but they turn out to have the same equivariant cohomology ring. So we can still use Panyushev's result in that case. And so we have the same diagram in the minuscule case for any other types. And finally, I just say that this generalizes partly conjecturally to all irreducible representations. So we will be able to construct the bundle of algebra structure on the universal bundle in any representation. And then you can even just take away my motivation, which is my interest, the mirror symmetry for Hitchin vibrations, and what you are left here around can just be thought of in this generality as some sort of classical limit of the geometric Satake equivalence, which is still under, we are working on this. But then this way we are going to have a very nice circle of ideas again, which includes a new way to think about equivariant cohomology in terms of coordinate rings of certain fixed point schemes, also constructing universal bundle of algebra structures using Kirillov algebras. That means the whole representation theory of reductive groups. And finally, everything is done through the Hitchin system. So it's again a nice circle of ideas. And we hope that even we will be able to extend these ideas to real groups and representations of real reductive groups, and also perhaps applications to arithmetic are not impossible, because arithmetic is everywhere when you study affine Grassmannians. So I thank you for your attention.